Hi, I'm Robin, and today we're going to talk about one of the colligative properties, namely Raoult's law. So, what are colligative properties in the first place? First of all, these are properties that have to do with solutions. And specifically, they're properties that change depending on the concentration of the solute in your solution. And so, anytime you see the word colligative properties, know that this is a property that will intensify as a concentration increases. So this particular colligative property that we're talking about today, Raoult's law, has to do with the vapor pressure of a solution. So normally when we think about a liquid turning into a gas, we think about, putting a pot of water on the stove and making it boil. And if you do that, then all of the water will go away. But if you think about it, even at relatively low temperatures, if you put a glass of water on the table and you just leave it, over time, the level's going to drop, right? And eventually it'll all disappear. So somehow, without hitting the boiling temperature, we actually have vaporization going on. We did talk about vapor pressure earlier when we were talking about intermolecular forces. I've linked that video below. But what we're going to talk about now is not a pure liquid that's evaporating, but rather some sort of solvent that has something else in it. Now that something else does not have to be a solid, although that is the first thing we think about when we think about solutions. But remember, solutions can be anything dissolved in a fluid. So sure, it could be a solid, it could also be another liquid. And in fact, as you'll see, when we talk about Raoult's law, we could talk about multiple liquids that could be evaporating simultaneously. So here's the equation that accompanies Raoult's law. And this is the official way that we write it. The partial pressure of a solution equals this big mass. Well, what does this mean? Remember, this symbol is a summation symbol. So basically what we're going to do is we're going to calculate a whole bunch of things and add up the results of each of those calculations. How many things are we going to add up? Well, that's given by this number here, and that number basically tells us the number of volatile components in solution. What's a volatile component? Something that can evaporate, something that has a vapor pressure. So that's generally going to be any liquids in the solution. All right, so we're doing this calculation for every single volatile component in a solution, and we're going to add up the results of all those calculations. What is that calculation in the first place? Well, we're basically multiplying two things together. The first thing is the mole fraction of whatever that volatile component is. I put liquid here. It's usually a liquid, so we're just going to assume that. The second thing that goes in here is the vapor pressure of the pure liquid. So that is the vapor pressure. If you took that one volatile component and you had it all by itself, what would its vapor pressure be? So if you do those calculations for every volatile liquid and you add it up, what you're going to get is the vapor pressure of the entire solution. Again, this is the sum of any number of volatile things. We could have 10 or 20 different liquids at a time that are all mixed together. And so you will see Raoult's law written multiple ways, but they all come back to the same basic formula. So for example, if you have two volatile components, you might see a form of Raoult's law that looks like this. That's because we're doing two different calculations and we're adding those two calculations together, right? We could put 3 and then we're going to do 3 calculations. We can also do 1. And you might say, 1? Why would we do a calculation for 1? Isn't that just... Well, no, because sometimes you have a solution that has a solvent that's volatile, and then it has a whole bunch of non-volatile solutes mixed in. Take, for example, seawater. I mean, that has like sodium and chloride and bicarbonate and potassium and sulfate, all sorts of stuff mixed in there. None of those things evaporate, right? You've never seen salt evaporate if you stick out the salt shaker on the table. So really, we're just calculating how fast does the water evaporate. And so that's when you'd use the one-term version of Raoult's law. So let's use Raoult's law. Let's put it into practice. And the first thing you're going to do when you do this is you're going to look at your solution and figure out how many components are volatile, and specifically which of those components. Then you're going to go through the solution component by component and figure out how many moles you have of each component. That's true whether you're talking about a volatile component or a non-volatile component. You still need to know how many moles. Because the next thing you're going to do is you're going to calculate the mole fraction of every volatile component. Remember, to do the mole fraction, you have to do the total number of moles in the mixture. And so that's why you need the moles of non-volatile components. And then the last thing you're going to do, you're going to take those mole fractions and you're going to plug them into a Raoult's law. So here's the sort of Raoult's law problem you might get. Basically, calculate the vapor pressure of a solution with two different volatile components. In this particular case, we have water and hydrogen peroxide. So let's go through those 4 steps I pointed out earlier. Remember, the first step is to determine which components of the solution are volatile. Now, people do ask me, how do you know? And I'll tell you how you know. If you get a question that says the P naught of this thing is, okay, the P naught, remember, is the partial pressure of a pure liquid. If you have something that has a vapor pressure given to you, that tells you it vaporizes. It tells you it's volatile. So basically go through and look and see which of those things have an associated vapor pressure. Now, if you were doing a Raoult's law calculation for something which, is in your laboratory, so no one's made up the problem for you, what you can do is just assume that if it's a liquid, it's going to have a vapor pressure. And you can look up the vapor pressure at particular temperatures online. They have these things in tables. You can often even find a lot of data on Wikipedia nowadays, so it's really easy to find. All right, so in this case, both of our solution components, both water and hydrogen peroxide, have a vapor pressure, and so they're both volatile. The next thing is to determine how many moles of each solution component you have. In this particular case, I've given you the number of moles in the problem, so we don't have to calculate it. Don't worry, we'll do that for something else later. And then the third step is to calculate the mole fraction of every volatile component. So let's start off with water. Remember that the mole fraction is given by the number of moles of whatever you're calculating the mole fraction for, divided by the total number of moles. So for water, we have 8.7 moles, and the total number of moles in the solution are 8.7 moles of water, 12.3 moles of hydrogen peroxide. So let's run the math. We get 0.414 for our mole fraction. For hydrogen peroxide, same sort of calculation, except now we have 12.3 moles of hydrogen peroxide divided by the same number of total moles, and that gives us 0.586 for our mole fraction. Now, if you only have 2 components, you can actually skip that second calculation because your mole fractions always add up to 1, remember? And so we could just do 1 minus the mole fraction of water, and that would give us 0.586 as well. So you can check my math on that, but that's how it goes. All right, so now we have our mole fractions. We can plug those into Raoult's law. We have 2 volatile components, so we have a 2-term version of Raoult's law. So let's start with the calculation for water. For water, we have a mole fraction of 0.414, and we have a partial pressure of pure water of 23.8 torr. For hydrogen peroxide, then, we're going to have a mole fraction of 0.586 times our partial pressure of 1.97 torr. And if you run that calculation, you'll see that our vapor pressure is going to be 11 torr. Does that make sense? Yes, it should be between the vapor pressure of pure water, 23.8 torr, and hydrogen peroxide, 1.97 torr. Okay, so that was pretty simple. Let's do something that's a little more complicated. And what's a little more complicated than a 2-term Raoult's law problem? A 3-term Raoult's law problem. So we're going to do this exactly the same way. Here we've got 3 different liquids, water, ethanol, and acetone. Which of these components are volatile? Well, let's see. All 3 of them have a vapor pressure associated with them. That means all 3 of them are. Again, for step 2, I've already given you the number of moles in this problem, so we're just going to plug in the number of moles that are given. And then step 3 is to calculate the mole fraction of every volatile component. For water, we have 12.4 moles divided by a total number of moles of 12.4 plus 7.1 from the ethanol and 5.5 from the acetone. So we run that through the calculator, it's 0.496, just about half of the solution. For ethanol then, we're going to have 7.1 moles of ethanol, same total number of moles. What does that give us? 0.284 for our mole fraction. Acetone, we have 5.5 moles, same number of moles total, and that's going to be 0.220. Again, if you add up all 3 of these mole fractions, they equal 1. So that's the way you double check that you did your math correctly. All right, now that we have our mole fractions, we can go ahead and we can calculate the vapor pressure of the solution using Raoult's law. And again, 3 volatile components means we do 3 calculations. We have a 3-term form of Raoult's law. So let's start with the calculation for water. Remember water, we had a 0.496 mole fraction times 23.8 torr for pure water. Now for ethanol. For ethanol, we had a 0.284 mole fraction. 44.6 torr is the vapor pressure. And finally, for acetone, which has a very high vapor pressure of 181.7 torr, we have 0.220 mole fraction. Now let's check our math. We've got 64.4 torr for our overall vapor pressure of the solution. So this particular problem looks a little different than the way the other problems were laid out. We're given the vapor pressure of pure water, 23.8 torr, so that part looks familiar. But then it asks us for the vapor pressure of a saltwater solution containing sodium chloride and water. So which of those components are going to be volatile? We know that water has a vapor pressure, it must be volatile, but we don't see a vapor pressure for sodium chloride, and we know that salt doesn't really evaporate very easily. So we're just not going to deal with that. We only have one volatile component. The next step is to determine how many moles of each component you have for the solution. Now, we've always skipped this step in the past because I've always given you the number of moles, but here we have the number of grams, right? So we have 13.5 grams of sodium chloride. We need to turn that into a number of moles of sodium chloride, and for that we're going to use the molar mass. The molar mass of sodium chloride is 58.44 grams, and if we do our calculation, we discover that we have 0.231 moles of sodium chloride. How about water? Again, we're not given a number of moles of water, we are given a mass. So we're going to take that mass and we're going to use the molar mass of water as a conversion factor to give us the number of moles, 5.52 moles of water. Great, so now that we have the number of moles, we can calculate our mole fractions. And we're going to do this exactly the same way. For water, we have 5.52 moles, and the total number of moles we have is 5.52 from water and 0.231 from sodium chloride. That gives us a 0.96. Now you can see that water is, in fact, the major component of the solution. Now, how about the mole fraction for sodium chloride? Well, we don't have to do that because it's not a volatile component, right? So let's go ahead and let's plug this into Raoult's law. We have a one-term form of Raoult's law. Here we go. And so the vapor pressure of this solution is going to be 0.96, which is the mole fraction of water, times the partial pressure of water, 23.8 torr. And that gives us 22.8 torr, right? So what does this tell us? This tells us that salt water is not going to evaporate as quickly as pure water. There's going to be less water molecules in the atmosphere over a saltwater solution than there would over the same amount of pure water. So that's Raoult's law in a nutshell. It's basically talking about the vapor pressure of a solution and how that's dependent on concentrations of what's in the solution and whatever the vapor pressure is of each volatile component. So I hope that was helpful. Continue on to learn about some other colligative properties.